Docker format container size is an interesting topic in 2025 because there are four emerging trends for reducing Docker container size. So first up, let's talk about why would I care about reducing container size. So one of the reasons is it's going to cost you a lot less money to have a small container. You can see in Python, many containers could be 5 GB. And I think there's some confusion about development versus production. Also, if you look at the ultimate endpoint, if you can get it down to, let's say, under a megabyte, which is actually possible, you could get incredible performance and you could containerize many parts of your application. So let's really talk through why you would care about some of these container types, what they are, and then go through step by step. So first up, we have a Scratch container. A Scratch container is basically a minimal attack surface. And let's go ahead and describe in a nutshell what it is. This is the absolute minimal base image. It's literally an empty file system. So you can think of it as nothing in the container world. There's no libraries, no shells, no utilities. Now, let's also talk about why these modern compiled languages play nice with Scratch containers. So again, 0 MB. So Rust and Go in particular are really nice because all of the dependencies are built in. They don't need anything else. So the pros are, this is the smallest possible size. It leads to faster downloads, uploads, and deployments. Also, minimal attack surface. So there's really nothing to attack. It's just the binary itself. This is the highest level of security because there's nothing to exploit. And you are very explicit about what you're putting inside of there. Some of the cons would be that you would have to have statically linked binaries. So you can't do dynamic linking of shared libraries. There's no shell or debugging. This could make troubleshooting harder. And also it's going to require sophistication, right? You have to manually add required files like configuration files or certificates. But really the canonical example would be a single statically linked Rust executable is copied into a Scratch container. That container only contains that executable. So that's a very compelling case if you're using systems that launch containers, for example, on AWS, ECS, or Kubernetes, an open source container launcher. Next up, let's talk about Alpine. Alpine, the base is 5 MB. What would we care about this? Well, it's a very lightweight Linux distribution built around musl, libc, and also busybox. The goal of it is it's a security and simplicity and resource efficiency design. And it's also something that includes a base set of utilities and a package manager, APK. So the use case is that it's a base image that you could use that's a small, secure, but still functional Linux environment where maybe Scratch is too restrictive. It could be good for applications that use dynamic linking and require a shell for occasional debugging. So the pros are extremely small size, significantly smaller than traditional distributions like Debian or Ubuntu, security focus, so it's designed with security in mind. Also, APK makes it easy to add additional tools, and a shell, the debugging and interactive tasks are easier. The cons are you have to have something that's compatible with the musl libc. Also, there's going to be a smaller community than Debian and Ubuntu. And a good example would be that if you're going to install something with Python, maybe you could look at using Alpine. In terms of distroless, this is a middle ground here where it's a 10 MB base image. It's a set of images that Google created that have only the minimal runtime dependencies for a specific language like Java, Python, Node, Rust, etc. They don't have a shell. There's no package manager. But this is really a use case for the minimalism of Scratch, but also the convenience of a pre-configured runtime. This would be ideal for applications that don't need a shell. The pros would be it's smaller than a full distribution, reduced attack surface area, so no shells or utilities. It's got language-specific optimizations, and there's no need at all for these package managers. The cons are no shell, debugging is going to be harder, so that's similar to Scratch. Limited support for other languages that are not specified, and also a little bit less flexible, could be a little bit harder. but a good use case could be like a Java application packaged as a jar. Now, the final one is Debian Slim, which is about 60 megabytes, which is still pretty small. This is a stripped down version of Debian Linux, and it includes a core set of system libraries and utilities like a shell, bash, package manager. This is if you need a more complete Linux environment than, let's say, Alpine or Distrolist, but want a smaller image. You're going to have a lot of pros here, like a larger community. People know Debian, familiar environment if you use Debian or Ubuntu, apt package manager, also good compatibility. So the cons would be a larger size, so it's going to be bigger than Alpine or Distrolist, so it's going to be a slower deployment, slower invocation, also a larger attack surface area. So this would be if you're building a very complex environment, maybe Debian Slim comes into play here. So really the trade-off here is between size, security, ease of use, and compatibility. And with Scratch, it's the smallest, most secure, but most restrictive. Alpine is small, secure, and fairly flexible. Distrolist is small, secure, and language specific. And Debian Slim is larger and less secure, but more familiar. So in a nutshell, really why would we care about some of these things is that if you're looking at building very efficient, energy efficient systems, very secure systems, this is where both Rust and also Zig come into play. And also it points out how some of these scripting languages like Python really are starting to show their age, because Python is dependent on really running inside of an environment that is an operating system. A binary doesn't need those same kinds of things. And so we see like a weakness in Python in that it doesn't have the concept of a binary. It doesn't have the concept of a compiler. But if we look at things like Go and Rust, the strength of this standalone binary makes it so that it's very efficient to deploy services at scale. And it gets even more clear when you get into languages like Zig, for example, which is a modern replacement for C, that you can build extremely small binaries by optimizing certain flags. For example, you can say, I want to strip out any kind of efficiency for single-threaded programs. I want you to strip out the symbols so that I don't care about debugging it, et cetera, et cetera. And you could get maybe like a Scratch container with a minimal binary that's, let's say, 50K, right? And it could do something useful for your organization. And this could fit really well onto a Raspberry Pi or an ARM system or some kind of embedded system. And so there's a lot to like about building these really tiny, very energy efficient systems, and also having them run potentially inside of invocation services like AWS Lambda or Kubernetes or ECS. I guess really the takeaway here is that the new paradigm is how small can you get a container, and can you get it under 1 megabyte? And then can you use languages like Zig, or can you use languages like Rust to really just tweak that last bit of performance, that last bit of security, and optimize and create new solutions that weren't available without these very efficient container-based workflows that we have now?